Okay, we're talking about, this is 2.2, graphs of polynomial functions of a higher degree, meaning it's higher than squared. Generally, we're going to be talking about equations that are maybe to the 4th power, 5th power, something like that. As we talk, I'm trying to share the screen, hang on. As we talk about our different functions, okay, you're going to have a quiz on next Tuesday. And it's going to ask you a whole bunch of things about one equation. It's going to ask you about the zeros. It's going to ask you about the terms, multiplicity, that sort of thing. Math computation-wise, there's not a lot that goes along with this. The most you're going to have to do computational-wise is factor in this section. But you're going to have to know what to look for and where to look to find like the end behaviors of graphs, to find multiplicity, that sort of thing. So this beginning, the first few slides, just talking about what it means to be continuous versus discontinuous. So a continuous function, guys, has no breaks, no holes, no gaps. Okay, so this is continuous because there's no breaks, no holes, no gaps. This is not. This is called discontinuous because there is a gap. There's a break in the domain or the range. We're looking at the next feature they talk about smooth rounded curves. All right, when you are graphing a polynomial of a higher degree, it's a function, it has smooth rounded curves. As you notice here, this has a sharp turn. So these are not polynomial functions. This sharp turn would be the absolute value of x. It makes a v. So you just have to kind of pay attention to that. That's out there. This slide says a lot, but what it mainly is saying is the greater the value of n, the bigger your exponent, the flatter the graph is near the origin. Now, we're not going to be graphing these right now, so you don't really have to worry about that, but n is what we're going to be talking about as our exponent. We're going to be talking about polynomials to a higher degree, meaning to the 4th power, 5th power, 6th power, and they're always going to refer to n as the exponent that we're talking about. Okay, I want to talk about some stuff here. When you have an even function, okay, we've talked about even before, even and odd. When we have an even function, guys, even, right? What's happening with the arrows in an even function? Arrows at the end of the graph with an even function.
They're going the same way.
They're going the same way. You need to remember that. Even is same. When you have a function that is odd, all right, the arrows are going in opposite directions, okay? That's very, very, very important to remember because you're going to have stuff that's x to the 7th power. You guys don't know what that graph looks like, but you have kind of a visual picture. Anything that has n, which is your exponent, as an even number, like 2, 4, 6, 8, it's going to resemble a parabola, meaning the arrows at the end are going to go in the same way. If you have x to the 4th, it might look like this when you graph it, right? It's not exactly a parabola, but notice that the arrows are going in the same direction. When you have a graph that has the highest degree is an odd number, it's going to resemble the cubic function. Not exactly like that, but it's going to have directional arrows that are opposite of each other. Does that make sense? Does that make sense, guys? Even, same, odd, opposite, okay? That's what we really need to take from this. We're also going to be talking about turns in the graph. Like, say I have my function and I graph this, right? Just say this is a turn, this is a turn, this is a turn, this is a turn. That's what they mean when they talk about turns in a graph. The way that you figure out turns or bumps in a polynomial function is you take n, which is the highest exponent, minus 1. So if I gave you an example and I said, okay, here is my function. I have negative 3x to the 7th plus 6x squared minus 1. And I said to you guys, how many turns does this graph have? Like if you had to pick the graph from here, you can
6.
pick how many turns it has because you would look at the highest exponent. Very good. You look at the highest exponent, which is 7. So you'd say 7 minus 1. It has 6 turns or 6 bumps in it. Kind of gives you a visual picture of what it might look like. Now think about the ends of the graph. Are they the arrows? Are they going to be going in the same direction or opposite directions?
Opposite.
Opposite, because it's an odd number. Okay, good. Okay, so we're not going to worry about this one now. We're not going to sketch them by hand. All right, these next two slides are super, super, super important. Super important. It's talking about end behaviors of a graph. What's the graph doing at the end? Using the leading coefficient test. I'm going to give you examples of equations, and I'm going to say, tell me what the graph looks like at the end. What's the end behaviors? And in a couple minutes, you'll be able to do that. When n, remember n is your highest exponent. When n is an odd number, your arrows will be going in opposite directions. Everybody see that? Yes or no?
Yes.
Okay, so depending if the leading coefficient is positive or negative is going to tell you what the end behavior is. If the leading coefficient is positive, you'll say that the graph falls to the left and rises to the right. Think about a positive cubic function. We always read from left to right, so you look at the left-hand side first, then the right. If you have a negative leading coefficient, that means it's going to slope downwards. So on the left-hand side, your graph is rising. On the right-hand side, your graph is falling. Now, I know some of you are going, wait, what? Just give me a second. It'll make a little more sense. We'll do some examples. If I look at this next slide, this is easier. When your leading coefficient has an exponent, your n, that's the highest exponent, is even, then you know that the direction of the arrows are the same. If it's a positive leading coefficient, they're both going up, so they're both rising. If it's a negative coefficient, then they're both falling. Okay? So let's examples that I wrote down here. Let's look at this one first. If I said to you guys, okay, tell me the end behaviors of this graph. First thing you look at is the highest exponent. So circle that exponent and say to yourself, actually write this down. Is this an odd number or is it an even number? Is 3 odd or even?
Odd.
Odd. So when I see odd, I think of the word opposite. I know my arrows are going in opposite directions, correct?
Right.
Okay, correct. So now I'm going to think, all right, look at the leading coefficient. If it's an odd function, it's going to resemble the cubic graph, something like that. But since this is negative, which way would the graph slope if it was negative? From left to right, which way would it slope?
Downward.
It would slope kind of like this. So to tell me the end behavior, you read left to right. What is the left-hand side of this graph doing? Is it rising or is it falling?
Falling.
Which way is it going? Is it going up towards?
Rising.
So you would say it's rising on the left. So you'd say rising left. And what's it doing over here on the right-hand side?
Falling.
It's falling right. Good. Now, once we do these next couple examples, you guys are going to be like, oh, okay, I get it. Look down here. Copy these. I don't think these are these on your paper? All right, so first thing we're going to do is I want you guys to tell me, talk me through how many turns or bumps would this graph have if I were to graph it? How would I figure that out? What's the highest exponent you see? 12. So to find out how many turns or bumps, you say n minus 1. So I'd have 11 turns or bumps. So it'd be like this, something like that. All right, now we're going to talk about the end behavior. I'll write out end behavior now, and then I'll just always put EB. The end behavior of this graph. So we have to look at a couple things. We look at the leading coefficient, and we look at the degree, the n. So what do I notice that the highest exponent is, odd or even?
Even.
Okay, it's an even number. And when I say even, I think same or opposite?
Same.
Same. Okay, good. Now, it's going to resemble a quadratic in the meaning that both arrows are going in the same direction. So are both of my arrows going to be going upwards, or are both of them going to be going downwards?
Down.
Why both down? I agree, but why?
Because it's negative.
Because my leading coefficient is negative. Good. Very good. So you guys would look always left to right. So I look on the left-hand side. Is that arrow falling or is it rising?
Falling.
So you would say falling left. And then I look at the other arrow and what's it doing?
Falling right.
Falling right. So right now, these two questions, say this was on a quiz and I said to you guys, all right, tell me how many turns in end behavior. There's absolutely no math computation involved. You guys have to know where to look if you're going to determine how many turns and what the end behaviors would be. Does that make sense? You guys with me?
Yes.
Wait, Miss Meadows,
Talk to
I'm
me.
confused on something.
Okay.
I'm kind of confused on where you got like the arrows going like the opposite. Like I know is it because of the negative?
Opposite and same direction of the arrows is based upon the exponent. It's the highest exponent.
Yeah, that I know.
Okay, so then the negative tells you if it was positive, both of them would be going up. Since it's negative, they're both going down.
Okay.
Yep,
Yeah,
that's-
I just wanted to make sure.
Yeah, that's fine. Good question.
Thank you.
Sure. All right, look at the next one. How many turns?
8.
How'd you get 8?
You subtract 1.
Perfect, good. Take the highest exponent, subtract 1, very good. Now I look at that exponent and I say, what kind of a number is 9?
It's an odd.
It's an odd number, so when I see odd, I immediately think opposite. If you guys are asking me on WebAssign, well, how am I supposed to show work for this? I'm showing you how to show work. You guys are thinking. So an odd function, guys, generally follows the pattern of a cubic, which slopes. I wrote what I need it to look like in a second. Generally looks like a cubic function that slopes upwards, right? But this is what kind of a number? Five. Negative 5? 5. Which one is it?
-5.
It's -5. So think about a line or a cubic function. If it was negative, it's going to slope downwards like this. So what's happening right here on the left-hand side of the graph? Is that graph rising or is it falling?
It's rising.
It's rising on the right. So you guys would tell me rising right.
Wait, isn't that left?
Yes. Sorry. Thank you. See, you guys are paying attention. That's good. Rising left, and then what's it doing on the right?
Falling on the right.
Perfect. Falling right. Good. Very good. All right, don't get fooled on this one. What's the highest exponent you see?
7.
7. Just because this x squared is in the front doesn't mean that's the highest. You have to make sure your function is written in standard form. Always look for the highest, the biggest exponent. So how many turns, folks, am I going to have for this?
6.
6. Where'd you get 6 from?
Because you do 7 minus 1.
Perfect. And now we're going to talk about our end behaviors. End behavior. What kind of a number is 7?
It's odd.
It's
Odd.
odd.
Going opposite directions.
Good. Opposite directions. Good. Now look at the leading coefficient. It's 5. Is that positive or negative?
Positive.
So it's going to resemble a positive sloping cubic function. It's going upwards because remember we read left to right, so it's going upwards. So what is happening over here on the left-hand side of the graph?
It's falling.
So you would write falling left, and what's happening on the right-hand side?
Rising on the right.
There you go.
Miss Meadows, does it matter which one you write first?
You always want to write from left to right. Good question. If this confuses you about drawing the cubic, what's another odd function that you guys are super familiar with? A linear, right? Linear function is x to the first power? Yes? Guys?
Yes.
So a positive line looks like this. Agreed?
Agreed.
And a negative line looks like that. Agreed?
Mm-hmm.
You can do the same thing here. Look, this would be falling left, rising right. This would be rising right, falling left. You can do it with a linear function too, if you want to. Just for a visual of what your arrows are doing. We've talked about this 5,000 times. A zero is the same thing as a solution. It's the same thing as an x-intercept. It's the same thing as a root. All those things mean find the zeros, find the solutions, find the roots, find the x-intercepts. The way that we do that is by factoring. Write that down, circle it. If you've ever had me for another math class here at Archbishop McCarthy, you've heard me say factoring is never, ever, ever, ever going away. This is the math computation that you're going to have to do from any problems that we look at. You're going to have to factor. Guys, if you're going to tell me I'm not good at factoring, you got to get good in a hurry. We're not going to go back through how to factor, when to do what. You guys need to know how. So if you have a question that looks like this and it says find all the real zeros. First of all, real zeros means they're not imaginary. So if you have a question that says find all the real zeros and you find some that are real and some that are imaginary, they only want the ones that are real. Sometimes it'll say find all the zeros. You just have to pay attention to what they're asking. But if they ask you to find the zeros, all that means is we're going to factor. So x cubed minus x squared minus 2x equals 0. What is the first thing we look for every single time we factor? Take out the GCF. Is there a letter and or a number that I can take out of every single term?
1, x.
X. So if I take out that x, guys, I'm not taking it out. I'm not removing it from the problem. I'm factoring out. I'm bringing it out in front, and then I'm reducing every term by x. So I'm left with x squared minus x minus 2 equals 0. Can I factor more? Are there factors of -2 that multiply to give me -2 but add to give me -1?
-2, +1.
-2 and +1. So now I can set each little piece equal to 0, and I can find my x-intercepts, my solutions, my roots, however you want to call it, I can find them. So I have an x-intercept or a root or a solution or a 0 at x equals 0. I have one at x equals +2, and I have one at x equals -1. Questions? How many turns is this graph going to have?
2.
2 turns. It's going to resemble what kind of a function?
An odd one.
An odd function, and it's positive, so I know it's going to go like this. So what's happening on the left-hand side? What's happening on the right-hand side?
It's falling on the left and rising on the right.
Perfecto. Falling left, rising right. You're going to have a question on your quiz that's going to ask you, tell me how many turns, tell me the end behaviors, tell me the zeros, tell me this, tell me that. Most of the stuff you can tell just by looking. The only thing you're going to have to do mathematically is factor. Does that make sense? You guys okay with the factoring there? Guys?
Yes.
Thank you. Okay. Now we're going to talk about multiplicity. A repeated 0 is multiplicity. My children are a product of multiplicity. I had 2 at one time, right? When we talk about multiplicity, there's two different things you're going to see. If you have a repeated 0 an odd amount of times, meaning if you have the same answer for x once, or 3 times, or 5 times, it says something about the graph. If you have the same answer a repeated number of times and it's an odd number of repetitions, then you're going to say that your graph is going to cross through the x-axis at that point. If you have, now think about this, if you have an even number, say I get x equals 2, x equals 2, and x equals 1. Do I have a repeated 0 in that case? Do I have the same answer more than once?
Yes.
I have a repeated 0, correct? How many times is it repeated?
Twice.
Twice. That's an even number, correct? Not that 2 is even. The fact that it's repeated twice is an even number. Then that means at the x-axis, your graph is going to touch the x-axis and bounce. It's going to, like if you have an x right here, it's going to touch. We say touch and turns. It's going to go back the same way it came from. It's an easy way to think of even. It does the same. So like here, do I have multiplicity here? Yes. Do I have the same answer a repeated number of times? Absolutely. So now I look and I say, well, how many times is it repeated? It's repeated 3 times. So that means it's going to cross through the x-axis. If you have something that's repeated twice or repeated 4 times or repeated 6 times, it's going to touch and turn or bounce at the x-axis. Again, when you're asked to state multiplicity, it's just a matter of knowing, understanding what that means more when we do a problem. So let's do one. All right. If I want to find the zeros, that means I have to factor. So 3x to the 4th minus 4x cubed equals 0. GCF, what can I take out of both of these?
X cubed.
I can take out x cubed, and I'm left with 3x, minus 4 equals 0. Everybody agree? Yes or no?
Yes.
Okay. Now remember, I told you a little trick. This will tell you how many zeros you're supposed to have. So how many x equals should I have for this problem?
3, right?
4.
I should have 4. So I'm going to say x cubed equals 0, and then I have 3x minus 4 equals 0. When I solve this, guys, the cube root of 0 is 0. X equals 0. I'm really getting that answer 3 times because 0 times 0 times 0 is 0. And over here, when I solve this, I get x equals 4 over 3. So if you were asked to state if there was multiplicity, do you have the same answer more than one time?
Yes.
Yes, you have multiplicity here. Now, if I asked you what happens with the graph there, well, look at your multiplicity. How many times do you see x equals 0?
3 times.
3 times. Is that an odd amount of times or an even amount of times?
Odd.
So that means it's going to cross through the x-axis. Now, you guys will get better at this the more we practice it. I have 2 examples that I want to go through with you, and then we'll be done, and then you'll have some tonight on your homework. And I promise we'll go through everything in our homework before your quiz. Maybe if we can get to it tomorrow, it'll be great. If not, we'll do it on Monday. Okay, this next slide you guys don't have. So write it down for me, please, and we're going to do these 2 together. For this first one, I'm going to answer all these questions. First thing I'm going to say is how many turns are there? Well, where do I look for turns? Tell me what to do.
N minus 1.
N minus 1. So the biggest number, that biggest exponent is 3 minus 1, so I have 2 turns. Okay? N behaviors. I look at my biggest exponent. It happens to be what kind of a number?
An odd number.
It's odd, all right? So I know the arrows. Okay, do it again. Positive or negative?
It's positive.
It's positive. So which way is my cubic going to be going?
It's going upwards.
It's going upwards, right? So I would be like this. If you want to just draw a line, a positive line, that's fine. What's happening on the left-hand side of my graph?
It's falling on the left.
Falling left. And doing what on the right-hand side?
Rising right.
There we go. All right, zeros. What does that mean? How do I find the zeros?
You have to factor it.
So I'm going to say x cubed plus x squared minus 4x minus 4 equals 0. Guys, 4 terms. We need to group, yes? What can I take out of x cubed and x squared?
X squared.
And I'm left with x plus 1. What can I take out of negative 4x and negative 4?
Negative 4.
And I'm left with x plus 1. So I bring my x plus 1 out in front. And whatever's left over gets its own parenthesis. So I'm left with x squared minus 4. Can I factor that more, ladies and gents? X squared minus
Yeah.
4. That's the difference of what?
2 squares.
Yeah, so I have x plus 2, x minus 2. So my zeros, I have x equals negative 1, x equals negative 2, and x equals positive 2. Right? Because we set these equal to 0. Yes or no?
Yes.
So multiplicity, that's the next question we ask. Is there multiplicity? Do I have
No.
the same root repeated?
Yes.
Is it
Wait, so it goes by root regardless if it's positive or
correct?
negative?
Because these are two, good question. These are two different places on a graph.
Ah,
I only have one negative 1, I only have one negative 2, and I only have 1 2. So is there multiplicity? You guys would say none or no. Don't just leave it blank. So remember, if you have a root an odd number of times, like once or 3 times or 5 times, is it going to touch and turn? Is it going to bounce? Or is it going to go through the x-axis?
It'll go through.
It's going to go through x-axis. The only math computation you had to do was finding the zeros. Everything else was just knowing where to look in the equation and what to think about rising and falling and that sort of thing.
Miss Meadows,
Yep.
aren't there 2 x plus 1s though?
No. When you get to this point, this is the new GCF of your equation. This is a term right here, and then this is a term. So what you did was you just took out the common factor of x plus 1. Just like when we had x, there was an x in every single one of them. We took out the x and put it out in front. We didn't take out 3 x's. We just took out the 1.
Okay, gotcha.
So when you factor out the
great.
common, hold on 1 second. When you factor out the common parenthesis comes out in front, you just write it one time. Good question.
Okay, thank you.
When it says like the turn, shouldn't you say like there's like 2 turns, or you just say go through like the x-axis?
No. We said the turns up here. That's fine. And
Oh.
then at each intercept is what it's going to do. Is it going to touch and turn, or is it going to go through? All right, let's
Wait,
do
how
it.
did you know
Sorry.
if the line went through the x-axis again?
Because you have each root one time. If you have a root repeated an even number of times, 2, 4, 6, 8, that's when it would touch and turn. You only have one of each of them. Since you only have one's an odd number, it's going to go through.
Okay.
I promise, the more we practice this, the easier it'll get. All right, let's go. We can do this quickly. How many turns do we have in this one?
4.
4.
4. Where'd you get 4? 5 minus 1. Good. 4 turns. I can't spell. End behaviors. Is this, what kind of a number?
It's odd.
Odd.
Odd. So direction of the arrows is opposite. Look at your leading coefficient. Is it positive or negative?
It's positive.
It's positive. So what's my sloping cubic is going to be going upwards, right? Did I draw that right? You guys with me?
Yep.
So it's going to be doing what on the left?
Falling on the left. Rising
Falling
on
left and rising
Right.
right. Good. All right, now I have to find the zeros. Well, now I have to do some math because finding the zeros just means please factor. So x to the 5th minus 32x equals 0. Is there something in common that I can pull out of 2x to the 5th and 32x?
X.
And what else?
2.
Okay, so if I pull out 2x and I divide this out, I'm left with x to the 4th minus 16 equals 0. Can I factor that more?
Yeah, it's the difference of 2 squares.
It is the difference of 2 squares. So I have 2x, I have x squared minus 4, and I have x squared plus 4 equals 0. Can I factor that more?
X squared minus 4.
Yep. So I have 2x, and I have x plus 2, x minus 2. Can I factor this anymore?
No, because it's
No,
adding.
because it's adding. It's not the difference. So I have lots of little pieces that I have to set equal to 0, but I should have known that from the beginning because since my exponent is 5, how many x equals should I have?
5.
5. So I'm going to set every little piece equal to 0. X minus 2 equals 0. And x squared plus 4 equals 0. So here, I'm going to divide both sides by 2. I get x equals 0. Subtract 2 from both sides, I get x equals negative 2, right? Add 2 to both sides, I get x equals 2. Ooh, how do we do this one?
Subtract 4.
I'm going to subtract 4 from both sides. Good. So I get x squared equals negative 4. Now what?
Take the square root.
I'm going to take square root. When I take the square root of a negative number, ladies and gents, what's going to be in my answer?
It's imaginary.
It's imaginary. Good. And since I put the square root on top, Coach Check just walked in. He's making fun of me. Since I put the square root on top of it, what goes in front of my answer? Plus or minus, right? 2i. You guys with me? So these are all my zeros. I have 5 of them. I have 1, 2, 3, 4, and 5. How many real roots do I have? Not all at one time, guys.
3.
How many?
3, I think.
3. Alexa, you should be speaking up. Your dad's really proud of you. Come on. How many real roots do we have?
3.
3 real. There's a girl. How many imaginary?
1.
2.
2 imaginary. Okay, guys, do I have multiplicity? Do I have the same root more than one time?
No.
Yeah.
No, not exactly the same. So there's no multiplicity. If there's no multiplicity, what happens at the x-axis?
It goes through the x-axis.
Goes through x-axis. Super duper. How do we feel?
Miss Meadows.
Good.
Yeah, talk to me.
So